Welcome to today's lecture. We just want to recall that an important theorem that we had stated in the previous lecture was called Lagrange's mean value theorem. So, just have a look at the statement again, so that we are able to apply it properly. So, Lagrange's mean value theorem is about a function f which is defined on a closed bounded interval a b to R, and it has the following properties. So, we are given that f is a function on a closed bounded interval a b taking values in the real numbers. One, f is continuous on the closed bounded interval a b, and f is differentiable on the open interval a b. If these two conditions are satisfied by the function on the closed bounded interval a b, then the Lagrange's mean value theorem says there exists a point C belonging to a b such that the difference f b minus f of a is equal to f dash of C into b minus a. We can rewrite the last conclusion in case b is not equal to a as f b minus f of a divided by b minus a equal to f dash of C. So, this is Lagrange's mean value theorem, and geometrically it says the following. So, let us look at the picture. Lagrange's mean value theorem says that if satisfies those two conditions, that f is a continuous function on a closed bounded interval a b and differentiable in the open interval a b, then there is a point C such that the tangent at that point is parallel to the chord joining that points a f of a and b f of b. So, this is an important theorem in calculus which gives us a lot of applications. So, let us look at some applications of Lagrange's mean value theorem. First application says if f is a function on an open interval a b to R, and f dash of x, if it is differentiable function in open interval a b to R and its derivative is bigger than 0 for all x, and f is strictly then f is strictly increasing on a b. So, this we are saying that if a function is differentiable in the open interval and its derivative is strictly bigger than 0, then the function is strictly increasing in the interval a b. So, note this is a property of the derivative of the function on the whole of interval a b. So, if the derivative is strictly bigger than 0 for all x, then it is strictly increasing in a b, and similarly if f is f dash of x is less than 0 for all x, then the conclusion is f is strictly decreasing in a b, and finally if f dash of x is equal to 0, then f is a constant function. This is a very simple and straightforward application of the mean value theorem. So, let us just look at why this is so. So, we are given the function f on open interval a b to R, and we are given f dash of x is bigger than 0. Okay. So, f dash of x is bigger than 0. So, for all points f dash of x is bigger than 0 for all points x belonging to a b. So, we want to show this implies f is strictly increasing in a b. So, let us take 2 points x 1, x 2 belonging to a b such that x 1 is less than x 2, and we apply Lagrange's mean value theorem in the interval x 1 to x 2. So, that will imply that there exists a point C belonging to x 1 to x 2 such that f of x 1 minus f of x 2 is equal to f dash of C into x1 minus x2. Right. So, this is application of Lagrange's mean value theorem. Now, because x1 is less than x2 and f dash of x is strictly bigger than 0. So, this implies that the right hand side is bigger than f dash of c is bigger than 0 and x1 is less than x2, that means this product is always less than 0. So, implies by the given condition f of x1 minus f of x2 is less than 0, which implies that f is strictly increasing. So, this is the way Lagrange's mean value theorem will be used to prove various conclusions about the function. So, basically what we are saying is, if we know something about the derivative of the function, then we can always deduce some properties about the function itself. So, in the same way we proved it for f dash of x bigger than 0. Similar proof will work for f dash less than 0. And the last property is obvious, because if the derivative is equal to 0, then f of x1 minus f of x2 divided by is equal to f dash of c, which is equal to 0. So, the simple application of Lagrange's mean value theorem will not really go deep into the proofs. We will see how these things can be applied. So, here is the visualization of this last theorem. We have, so this is function, this is the graph of the function, and you look at the tangent at any point. So, on the left side the tangent will be like this. So, the slope of the tangent will be negative, right, because the angle will be more than 90 degrees. So, the slope of any tangent at any point will have a negative slope. That means the derivative is negative on this part of the graph. So, function will be decreasing, that as we can see from the graph also. And on the right hand side, as we cross this flat part of the graph, here that in this graph the derivative is equal to 0 actually. That means the tangent is horizontal, and as we go from left to right, the slope increases, and as a result you see that the function also is increasing. So, this is the way interpretation of the derivative being positive implies the function is increasing, and the derivative negative implies the function is decreasing is applied. So, now let us apply this tool to marginal analysis. Let us just recall that the marginal of a function was defined as the slight change in the dependent variable when the independent variable changes by 1 unit. So, for if the demand and the price functions are related by q is equal to a into p raised to power b, where a and b are constants. So, q is the demand, p is the price. Then we had defined what is called the elasticity of demand of the price, and we had defined it for general functions, and for this function we have computed in one of our earlier lectures, and we showed that it is equal to b for all p. So, elasticity of demand for every price was the constant, and that constant was equal to b for this function. So, for such a product, the total revenue, so let us calculate the total revenue for such a product where the demand is related with price this way. So, total revenue is defined as the price into the quantities PQ. So, P into Q the demand. So, that is the total revenue. So, it is A into P, the definition of Q is A into P raised to power B. So, we put that. So, this is A into P raised to power B plus 1. So, that is the total revenue. So, thus the marginal of total revenue will be the derivative, right. So, that was the definition of a marginal of a function, namely the derivative of the function at that point. So, marginal of the total revenue as a function of p will be derivative of total revenue with respect to p, and that will be marginal of revenue. So, that will be equal to a into b plus 1, the power comes down, into p raised to power b plus 1 minus 1. So, that is p raised to power b. So, marginal of revenue turns out to be a into b plus 1 into p raised to power b. So, now let us so for the if the demand function is this, then we just now saw that the marginal is given by this. So, what does this imply? So, let us look at the constant b. If b minus 1, okay, depending on b minus 1, the marginal will be positive or negative. So, if b is less than minus 1, if b is less than minus 1, then this quantity marginal revenue will be negative, because this b plus 1 will be b plus 1 will be a negative quantity. So, that will imply that the marginal of revenue is less than 0. So, what does this have implication? It says the total revenue as a function of the price will decrease. So, marginal of the revenue is negative. So, there will be a decrease. Marginal revenue is the derivative of the revenue. So, that says that the revenue will decrease as the price will total revenue as a function of price will decrease. So, revenue will decrease as there is a increase in the price. So, it is a decreasing function. So, if b is equal to minus 1, that means this will be equal to 0. So, then in that case the total revenue will be independent of the price, it will stay stationary, right. The marginal of revenue will be 0. So, there will be total revenue is independent of the price, and in case it is bigger than minus 1. So, total revenue as a function of price will increase. So, depending on this for this kind of demand related with price, depending on the p, the constant b, if b is less than minus 1, then total revenue if b is less than 1, total revenue will decrease. If b is equal to minus 1, the total revenue will stay stationary. If b is bigger than minus 1, then the total revenue as a function of the price will increase. So, that is the way we interpret the notion of marginal with respect to the total. So, let us also recall that the total revenue as we have seen earlier also is given by P into Q. So, this implies that the marginal of revenue, if we differentiate this, is d. Now, we are going to differentiate with respect to demand. Earlier, we differentiated with respect to price. Now, marginal of revenue with respect to demand, we are going to calculate in this. So, if T r is equal to P q, so if we find the derivative of total revenue, that will be marginal of the revenue. So, on the right hand side is P into Q, where P is a function of Q. So, function of a function, there is a product function. So, we apply the chain rule to find the derivative. So, derivative of total revenue with respect to Q will be product function. So, it will be Q into derivative of P dP by dQ plus the derivative of PQ with respect to Q. So, that will be 1. So, that is P. So, using the product rule and the chain rule, the derivative MR, the marginal of revenue, that is the derivative of TR, is the derivative at the right hand side. So, product rule gives you it should be equal to Q into dP by dQ plus P. If we take P out common, so that is 1 plus Q by P into dP by dQ. Here we are taking P in the denominator because price is always going to be positive, it is not going to be 0. So, there is no problem in that. So, now once it is so, we can just simplify this a bit further. So, it is P into this we can take it in the denominator. So, it is 1 over dq by dp into p by q. So, here we are using the formula that for the inverse function, right, dp by dq is equal to 1 over dq by dp. So, that is used. Do not mistake is as if we are treating fractions. We are using the derivative of the inverse function formula here to write this term as this. Well, so, basically the idea is that if you can either treat p as a function of q or q as a function of p. So, you can treat one as inverse of the other from that relation. So, we are assuming that whatever is the demand and price relation, that is a invertible function. So, this is possible. And now, this is a formula for coefficient of elasticity of demand. So, we put that value here. So, it is p into 1 plus 1 over epsilon d. So, we get a formula that marginal of revenue is nothing but is equal to p times 1 plus 1 over coefficient of elasticity of demand. So, since p is always bigger than 0, so that gives us that marginal of revenue will be bigger than 0 if 1 plus 1 over epsilon d is bigger than 0. So, this is from the previous relation. Let us just go back and see. So, marginal of revenue will be bigger than 0, p is always bigger than 0. So, if this quantity is bigger than 0. So, marginal of revenue is bigger than 0 gets related with the coefficient of elasticity, that marginal of revenue is bigger than 0 if and only if 1 plus 1 over coefficient of elasticity of demand is bigger than 0. So, as in our problems we have seen earlier, the coefficient of elasticity of demand is a negative quantity always. So, this means that marginal of revenue will be bigger than 0 if and only if 1 plus 1 over epsilon d is bigger than minus 1, right. It is 1 plus. So, if this quantity is bigger than minus 1, that is epsilon d is less than minus 1. So, marginal of revenue is bigger than 0 gets related with the coefficient of elasticity of demand in this way. So, marginal of revenue is positive if and only if coefficient of elasticity of demand is less than minus 1. And we had earlier seen in simple examples that the coefficient of elasticity of demand less than minus 1 means it is very the relationship between price and demand is very elastic, and that is reflected here. The marginal of revenue is bigger than 0. So, marginal of revenue will be increasing if coefficient of elasticity of demand is less than minus 1. So, because marginal of revenue positive means that the revenue will be an increasing function. So, revenue will be an increasing function if and only if epsilon this coefficient of elasticity of demand is less than minus 1. So, that is a conclusion of this. So, that means revenue will rise if epsilon d is less than minus 1. So, upshot of this analysis is the following, right. So, the revenue marginal of revenue positive means revenue will be rising, it will be increasing if epsilon d is less than minus 1. So, let us look at some more properties of functions which are applicable in economics, commerce and management. So, for a function in an open interval a b to r, a point C belonging to a b is called a point of local maxima. So, the property of C is being defined is it is called a point of local maxima if f of C is bigger than f of x for all x in a interval C minus delta to C plus delta around C. That means, locally in a neighborhood of the point C, f of C is the value f of C is bigger than f of x for all x in that interval. So, in that interval the function value is the largest. So, then we say it is a local maximum, and similarly we define a point C to be a point of local minimum if f of C is less than or equal to f of x for all x between c minus delta to c plus delta. So, local behavior of the function we are analyzing, that we are saying a point c on an open interval is called a point of local maxima if locally the function is bigger than or equal to the value of the function at the point c is bigger than or equal to all values at nearby points, and similarly it is called local minimum if the value at c is less than or equal to f of x for all points is in neighborhood of the point. So, the local maximum and local minimum. So, in a sense if you look at the picture, the graph of the function will look like there is a peak at the point c if I look at a nearby points, and this is there is a bottom out kind of scenario if this is a local minimum. So, what we want to do is find the criteria in terms of the derivative of the function, which will help us to analyze whether the point c is a point of local maximum or local minimum. So, you can call this as the turning points for the graph of the function, because if you look at the picture, the graph will look like as follows. So, if this is the point c, then if in a neighborhood c minus delta to c plus delta, if we look at all points nearby and this is the value of the function at this point, then in that neighborhood what we are saying is the value of the function. So, the graph should look like this. The value at this point f of c should be bigger than or equal to f of x for every x belonging to x minus delta to x plus delta. So, this is a kind of a peak. So, graph there is a turn is going up and then it starts turning down if you look at the neighborhood of the function, value of the function at the point c in a neighborhood. Similarly, if we look at if there is a delta such that in this interval c minus delta to c plus delta, we can say that the value of the function. So, this is the graph will look like the graph will look like, let us say like this. So, this is the value at the point c. So, that means f of c will be f of c is bigger than or equal to f of c is less than or equal to f of x for every x belonging to c minus delta to c plus delta. So, if I look at any point x here, the value is this value, or if I look at x, then the value is this value, which is bigger than or equal to, and if I look at this way, then the value here it is less than the value at this point, right. So, here the value is this and here the value is this value. So, that is what local maxima minima say, and graphically this means that there is a turning, or these are turning points for the local maxima minima, or you can say there is a peak and there is a bottom out for the function at that point. So, this is the definition of local maxima and local minima. So, we would like to know when can we say, if we know some property about the derivative of the function, then the function will have a local maxima or a local minima. So, the first result is saying that if c is a point of local maxima or a local minima and f dash of c exists, then f dash of c should be equal to 0. So, this is if the function has a derivative at that point, and so what we are saying is if the derivative exists. So, if this is the function and this is the point c and this is the value f of c, if at this point the function has derivative, that means in a neighborhood c minus delta to c plus delta, the function will be defined, because derivative implies it is a continuous function. So, the graph is a continuous function, and if the graph looks like this, that means f of c is a point of, if c is local maxima, then what should happen? Then the tangent at that point should be horizontal, right. The tangent at this point should be horizontal. And similarly, if at a point C it is a minimum. So, let us say it is a minimum at some other point. So, let us say at this point there is a minimum. So, graph goes like this, and at this point there is a minimum. So, in a neighborhood of that point the function is continuous. The function is continuous at that point. So, it is defined at all points, and derivative exists at that point, again implies that the derivative is horizontal. So, that is what this theorem is saying, that we will not prove this theorem, but we will just use this. This is intuitively the motivation for the theorem, namely if f is defined on an interval a b to r and C is a interior point, C is a point inside the interval a b, then if at this point C is a point of local maxima or local minima, either of it, then and the derivative exists, then the derivative must be 0. So, that means at a point of local maxima or minima, if the tangent can be defined mathematically saying the function has a derivative, then the derivative must be equal to 0. So, this is a necessary condition for local maxima or minima. So, because necessary in the sense that mathematically these are very important theorems which gives you necessary conditions, that if there is a point of local maximum or a local minimum and derivative exists. So, if local maxima minima exists and the function is differentiable, then the derivative is equal to 0. So, that is used in a way that if you want to locate the possible points where the function can have a local maxima or a minima, then the necessary condition being derivative is 0. So, look at the function, look at all the values where the function has derivative equal to 0, then these are the interior points possibly where the function can have local maxima or minima. So, this gives you the possible candidates. So, this is how this theorem will be used. So, in the next lecture we will analyze how we will locate points of local maxima minima. Out of these candidates, how do we decide which points are local maximum and which points are local minimum. So, we will look into this property in the next lecture. Thank you.